Hello students, so welcome to the session in which we are going to learn mechanics of fluids. Okay, this is very tough topic but very easy if you understand the core concepts, basics. If you understand the basics clearly, it is very easy to solve any kind of question out of this topic. Okay, so now let us start our session. See, what is meant by a fluid? Fluid means any object that can flow with a very little or negligible force if it is applied on its surface. So anything which easily moves without application of any major force, a minor force is sufficient to cause its to strain. Okay, so that is those kind of matter we categorize as fluids. In this fluid we will get two substances in it. One is liquid and another one is gas. So here for fluids they don't have any kind of shape but they have volume. In that they have volume but they take the shape in which we keep them. So the containing vessel shape it will take. Generally fluid we study in two parts, one is statics and dynamics. In dynamics, kinematics will also be there. Fluid dynamics and fluid kinematics comes under fluid hydrodynamics. Okay, that means the fluids which are in motion, we study about the fluids in motion, that is hydrodynamics. Whereas fluids at rest we study that the concepts when a fluid is at rest, then it is hydrostatics. What is thrust means? See, when any fluid when you keep water in a container, okay, the water in a container, it has got some mass, as it is a matter, it has got some mass and weight. Okay, so now it will exert this weight on the surface on which we keep it. So now this is the surface which is bearing this water. So now on this surface the weight will exert as a force or a thrust. Okay, so now the force is being being bared by this surface, right? So now this surface area, for example, if you look at this in 3D, so this is a tumbler or a glass vessel in which I am keeping water, now so now the water area, so this is water, so this is the area which is bearing this water. So all the weight will come onto this surface, all the weight of the water will come onto this surface, and this surface is holding this water, right? The surface is holding this water. So now whatever the weight that is being exerted by the water will be taken by this area, whichever I am shading here. This area is taking this thrust. Now in your 10th class or 9th class you might have studied about pressure. So pressure means what? So pressure is simply thrust upon area. So thrust upon area, that is which area we need to take. So there are many areas here. If you look at this, this is side surface area, top surface area, side surface area, but we need to take the area on which the force is normally acting. So there are many areas here. This is one area, this is one area, this is one area, and this is another area. Which area we need to consider for calculating the pressure is, so on which area the force is being acting normally. So this area you need to take. Okay, this is very important thing you need to keep it. This is the basic clarity you need to have. So whenever we calculate the pressure of liquid or a fluid, we need to take the area of the surface which is perpendicular to the action of the force. Okay, now here we know that this is force and this is area. So force by area is the formula. From the formula we can derive the unit of pressure. That is, for force the unit is Newton, for area it is meter square. So Newton per meter square is the unit as a unit of pressure. Also we call it as Pascal. Okay, scientist name Pascal. So we keep Pascal for 1 Newton per meter square. Alternatively, the CGS system, the unit is dyne per centimeter square. We know how to derive the dimensional formula. Force dimensions is mass into acceleration, and this can be written like velocity by time. So mass into velocity means what? Length by time, as I already told in the previous session. So then it comes as mlt power minus 2 for force. Again we are dividing here it with area, force by area. Area means what? L square. again L square. So L square will come up, it will become L to the power of minus 2, then finally it comes as ml power minus 1, T power minus 2 is the dimension of pressure. Very, very important. Dimensional formulas are easy to derive if you know the formulas clearly. Okay. Now, what are the characteristics of the pressure? See, Pascal's law. What is meant by Pascal law is when a fluid is at rest, when a fluid is not moving, then the fluid will exert the same pressure in all the directions equally. So any fluid particle, it has ability to move in all the directions equally. So it will not move in one direction. Fluid particle tries to move in all the direction equally. So that is the reason why it will exert the same pressure in all the directions. This property is called Pascal's law, but it is applicable only for fluid at rest, when it is at rest, because if it is moving, then obviously the pressure will be in only one direction, in the direction of high pressure. When there is one direction there is high pressure, another location there is low pressure, then obviously all the fluid particles will tend to travel in only one direction. So in this case it will not be applicable, but when a fluid is at rest, it has a chance of going in all the directions equally. So that is the reason why it exerts the same pressure in all the directions. That is called Pascal's law. Again I am telling you that the same force it is applying in multiple directions. So that is why here the pressure is not a vector, it is a tensor. Tensor means what? Same quantity having many directions. For a vector there will be one magnitude, one direction, one magnitude in one direction, but in a tensor, so one magnitude but different directions is called tensor. So pressure is tensor quantity. Okay. Atmospheric pressure, if you look at earth, so everywhere, if you see, if you feel when you are riding a bike, when you are riding a bicycle, when you are going by bus, so you feel the some pressure is hitting your face, right? So that pressure is nothing but atmospheric pressure. So atmosphere around us will exert some pressure on us, on every element on earth, like oceans, earth surface, human surface, any objects around you. On all the object surfaces there is a pressure that is continuously being exerted. That pressure is nothing but atmospheric pressure. Okay, see here at sea level, because the pressure is not constant when you move up. Why? Because see again I am telling you, this is a very, very important basic concept. You need to keep it in your mind all the time. Means, so when you are riding a submarine, or if you are inside moving into the water, see, simply pressure of water means, so see, whenever you are sitting on a water, you are sitting on water and moving down. So now this is the water surface. Let us take, this is the water surface. You are here, right? So you will be getting the pressure of water above you. So how much water above you, or how much liquid above you, that liquid can only cause pressure on your head. Okay, on your head, but not the water below you. When you move down, that means when an object is here, in this case, let us, for example, let us take an object. Let us take like this. This is a very, very important concept. If you understand this, it will help you a lot while doing many questions in fluid mechanics, right? So an object is here. So on this object there will be some pressure, right? On this object there will be some pressure. This pressure is because of this head or this amount of water present above it. So the pressure on this object is because of this weight of the water. If the same object goes down, then the weight column is increasing. The more water is present on the head of the object, means more pressure is being exerted by the water on the object, right? So the H is increasing now. This is H2. Let us take H2. This is H1. So H2 is more than H1. Then more weight is coming on to the object, causing more pressure on the object. In the similar manner, if you are moving, this is Earth. So this is atmosphere around Earth, right? We are here, somewhere here, right? When you are moving up the altitude, means somewhere you came here. Now, this much is the atmosphere above you. This much is the atmosphere above you. So when you are on the surface, this much atmosphere is on you. When you are going up, the amount of atmosphere above you is decreasing, right? Means what? The atmospheric pressure will decreases when you move up in the earth surface. So when you are moving up, the amount of atmosphere above your head will decreases, because of which you will feel less atmospheric pressure at greater altitudes. See here, at sea level, this is the value you need to remember, 1.013. This is very important value in 10 to the power of 5 Pascal. While doing the calculations, while doing any questions and all, no need to keep this 0.13 and all. 1 into 10 to the power of 5 is simply, it is 10 to the power of 5 only. You can take this as atmospheric pressure for your calculations part, I am telling you. And the same thing, atmospheric pressure and bar, both are synonymous units. 1 atmosphere, 1 bar, both are same almost. Okay, one atmosphere the atmosphere pressure can also be measured in terms of Hg, that is mercury. Generally we use mercury in barometer, manometer, everywhere. So because why we use mercury is a different scenario. Mercury has got less vapor pressure, and there are some abilities of mercury makes it a manometric fluid which is fit for measuring the atmospheric pressure, because mercury has got more density. So mercury's density is almost 13,600 kg per meter cube. Okay, this makes it, this is very heavier fluid, and its vapor pressure is very less. Its vapor pressure is very less. All these things you don't understand at this point of time, but we use mercury as a reference fluid for measuring the atmospheric pressure. So that is the reason why we represent the atmospheric pressure in terms of mercury, that is 76 centimeters of Hg or 760 mm of Hg. Okay, 760 mm of Hg. 1 mm of Hg we call it as 1 torr. 1 mm of Hg we call it as 1 torr. These are all units for measuring atmospheric pressure. Okay, now hydrostatic pressure. See, hydrostatic pressure is different. Okay, see, whenever I am explaining you the pressure in the previous slide, I am telling at the bottommost area, but according to this Pascal's law, I told you that pressure is exerted on all the directions. Okay, right now the side faces, whatever the side faces are there, these faces also experience pressure of the water. Okay, but this face experience a uniform pressure because it is having the fixed amount of water on it. But if you come this way, in this direction, when you are moving down, this person will have more water on his head, this person will have less water. This location, very less water is there on the top of this point. Likewise, the side faces will also be exerted by the pressure of the fluid, but it increases gradually when you move down. When you move down, it increases gradually. Okay, that means when you look at the side faces of the any object, the pressure distribution will be like this. That means pressure will be very zero at the top, because there is no water or there is no liquid above this surface, then there is no pressure. But when you move down, gradually the amount of liquid is increasing, means the pressure is also increasing. Likewise, the pressure gradually increases and it will be maximum at the bottom, which is equivalent to the pressure that this bottom surface is getting exerted. Okay, so the bottom surface faces a pressure of rho GH. The bottom surface faces a pressure of rho GH, the same pressure that comes at the side face at the bottom. In the same manner, this side face also, other side face, whatever the face, other side face also, it will be face the same scenario. It will be having gradual increment in the pressure, and it will be rho GH at the bottom. It will be rho GH at the bottom. This is the pressure distribution, hydrostatic pressure distribution at the bottom of the vessel and at the side faces of the vessel. Now, how to calculate it mathematically? See, now if you look at a vessel like this, at the top there is atmosphere, as I told you already. So there is atmosphere. So now atmosphere will exert a pressure on this surface first. So that pressure is called atmospheric pressure. I am representing it as P naught here. So the P naught is what? This is atmospheric pressure. Okay. Now in addition to that, when you are moving down, in a fluid, in addition to this atmospheric pressure, the liquid head, whatever the liquid head is there, it is adding some more pressure. What is that pressure value? Rho g into h. So the pressure value, so already at this surface we have got the atmospheric pressure. In addition to that, when we are moving down, additional pressure adds up to the existing atmospheric pressure because of the weight of this fluid column, which is equal to rho gh. So whenever we move down, the pressure increases, and the value is initially the atmospheric pressure plus whatever the column of the liquid above you, this is the pressure of that liquid column. Okay, this is a very very important formula. We use it at many points of time in this topic. So what factors that affects the hydrostatic pressure? See, when you move down, only thing, if you look at the formula, it is quite evident that only the height and the rho, so these two, the g is same everywhere on the earth surface, so that will not affect the pressure part. So pressure can be increased only when the density of the fluid increases, and when you move down inside the fluid, as well as gravity also varies at equator and at poles. In that scenario, gravity also affects the pressure on a liquid. Okay, so there is no term called area, amount, cross section, shape in this formula. That means what? So the pressure is independent. So whatever the shape of the vessel you take, I am taking here rectangular shape, like that. Any shape you can take, like trapezoidal shape or a conical shape. Any shape you take, the same thing will happen. The pressure will be same when a person is here. If the height of the liquid is same in all the cases, okay, irrespective of the shape, irrespective of the volume of the water, the pressure at this bottom is same always. The pressure is always rho g h. Okay, because we divide with area. If we go in deep, you may get confused. Simply understand that. So the cross sectional area will not affect, the shape will not affect, the amount of water inside the vessel will not affect, because in the pressure formula only we have got three terms, so nothing else. How this pressure formula came? Now you got the doubt, like, so how this rho gh came? Let us understand it now. Okay, how this rho gh came now. So I told you here, pressure is what? Force by area. Pressure is force by area. What is the force here? The weight of the liquid, right? Weight of the liquid. So what is the weight formula? So weight is nothing but mass of the water inside the container into gravitational acceleration. This is weight, right? By area of the cross section, we have to take the area at the bottom area. This area we need to take, so then I want to divide it with area. Okay, now mass can be written as volume into density into g by area. So area, this volume is nothing but what? This area, okay, understand it clear. This area into height of the water. This is the height of the water, so this is the height of the water, so this is the height of the water. So this area of this plane into height of the water is nothing but volume of the water. So now I will replace this volume term as area into height into rho into g by area again. So the area gets cancelled. So what is the formula I am getting for pressure? So pressure is equal to rho gh. The pressure formula is rho gh. Okay, now likewise we got this formula of rho gh. So in this rho gh, only rho gh can affect the pressure, nothing else. Okay, now so same depth, same pressure, I told you right now. So any shape you take, only height of the liquid column will decide the pressure. when you are moving deep into the sea, the pressure that the sea exerts on a sea vessel increases. If the submarine is coming top of the sea, it faces very less pressure. When it is moving down into the sea, it faces more pressure. So only thing varying here is depth. So when the depth increases, pressure increases, depth decreases, the pressure decreases. Okay. Now pressure at the same level, see if the pressure, see when you are measuring the pressure, okay, when you are measuring a pressure by any shape of a container, any shape you take, see here the pressure is same everywhere, here the pressure is same, here the pressure, because all are at the same height, all are at the same height. See, if you see all these surfaces are at same height. So any shape you keep, any shape, if a water is running in a pipe, so let us take water is running in a pipe, and you just opened the pipe at various locations and keep these kind of vessels in that pipe. In every location the water will be raised to the same level irrespective of the shape of the container you kept, okay, you kept at the opening of the pipe. Are you getting the point? So here pressure gets converted into a liquid column of a same height, okay. So there is no effect of a shape here. If you have any doubt, you can do it, experiment at your home by doing some sort of you take a bucket of water and you open it somewhere and you put different shapes there, everywhere you will find the same liquid column in all the directions. Means what? The pressure, if pressure is same, then the liquid will be raised to the same level in all the shapes of container whatever you keep. Okay, this is also very important basic point you need to understand. Again, another basic point you need to understand is gauge pressure. Gauge pressure means, so there is a pressure called atmospheric pressure, there is a pressure called atmospheric pressure. Now see, a gauge pressure is a pressure which is above the atmospheric pressure. So if a pressure, atmospheric pressure is there, atmospheric pressure is there, now any pressure above this atmospheric pressure, so above atmospheric, this is atmospheric pressure, any pressure that is greater than atmospheric pressure, that is taken as gauge pressure, that is taken as gauge pressure. So gauge pressure is nothing but, so pressure minus atmospheric pressure, pressure minus atmospheric pressure. In the previous slide what I have explained you, at the top there will be atmospheric pressure, in addition to that this pressure will add up, this pressure will add up. So this is above the atmospheric pressure, that means this is gauge pressure. This is what? This is gauge pressure. So the pressure which is above atmospheric pressure is considered as gauge pressure. Okay, that is gauge pressure. Now gauge pressure is all it is always a positive excess pressure, okay, above the atmosphere. This is a positive pressure, like a pressure in your cycle tube, or in a bike tires, or in a pressure inside a pressure cooker, the pressure will be more than outside pressure, so that pressure is also taken as a gauge pressure. So the pressure value which is more than the outside atmospheric pressure is called gauge pressure. Okay, now so let us do some problems to understand the concepts which you have learned so far. If the pressure at half the depth of lake is equal to 3/4 of the pressure at the bottom of the lake, then what is the depth of the lake? Now let us understand with the concept which we have learned so far. Now let us draw a figure of a lake. So this, let us take this is a lake. Okay, let us take this is a lake, and now the pressure at half the depth of the lake, half the depth, let us take this is half the depth of the lake. Okay, so now at this point there is a pressure, there is a pressure at this point there is a pressure. Let us take it as h by 2 now, with a pressure at half the depth of the lake. Okay, so now this is the top surface, right? So in this top surface there will be atmospheric pressure. So P naught plus, when you are moving up to this point, the pressure will be rho g h by 2. So this is the pressure value at this half of the path of inside the lake. Now this pressure is equal to 3 by 4th of pressure at the bottom. What is the pressure at the bottom? So P naught plus rho g h. Now solving this, so now P naught plus rho g h by 2 is equal to 3 by 4 P naught plus 3 by 4 rho g h. So now this can be written as 4 by 4 P naught. Now it comes here, it becomes P naught by 4, and this rho g h by 2 can be written as 2 by 4. Okay, 2 by 4, yeah, 2 by 4. It comes here, so it will become rho g h by 4. 4 gets cancels. Now P naught, as I told you, atmosphere pressure, you can take it as 10 to the power of 5. Rho is 10 cube for water, and G, let us take it as 10 for a while. H I want, so H is equal to 10 to the power of 5 upon 10 to the power of 4, that is 10 meters. So the depth of the lake is 10 meters. Like that we can do. Now the next question here. So two bodies are in equilibrium and suspended in water from arms of balance. Okay, now here weight of the first object will be equal to the weight of the second object. See, listen very carefully. It's a very wonderful concept I am explaining you right now. Now here, when you take any object's mass or weight inside water, there will be two things. One is the weight of the object, another one is the buoyancy force of the water or any liquid exerts buoyancy force. Okay, now what is buoyancy? Buoyancy is nothing but the force of buoyancy is equal to, I will explain this buoyancy in detail in the coming lectures. Right now I want to just write the formula: rho into g into volume of the object. Okay, so this is the formula for buoyancy. Now, so the weight minus buoyancy is the net weight of the object 1. In the same manner, weight minus buoyancy of the second object is the weight of the second object. Now inside the water both are getting balanced, right? Means what? The weights are same. So the weight here inside the water is weight in the air minus buoyancy force, right? Now weight in the air is 36 gram into, I am taking gravitational acceleration as 10, that is 360 grams or 360 gram force is the weight of this object in air, minus buoyancy is rho, density of the liquid. I am taking it in water, so density is 1 gram per cc. Okay, now gravitational acceleration is 10. The volume I want, the volume is what? Mass upon density, 36 by 9. That means this is 40. So 40, this is 4, sorry, 4. 40, 360 minus 40 is equal to, on the other hand, this is 48 gram. So 48 gram, its weight is 48 into 10 minus its buoyant force is rho for water 1 g 10, and the volume of the object I don't know, 48 by rho of that object, density of that object. If you balance these two, you will get the answer. So 360 minus 40 is 320, okay, is equal to 480 minus 480 by rho. Now this 480 by rho is equal to 480 minus 320, that is 160. 480 minus 320 is 160. So 160 rho means how much? 480 by 160, that is 3 gram per cc. Okay, this is the rho of the second object, right? And next question, inverted bell lying at the bottom of a lake. See here, a bell is immersed inside the liquid at the bottom, which is 47.6 deep, having air inside it, 50 centimeter cube. Now when I bring it to the surface, its volume of air is something else, V2, I don't know. So now I need to this, the depth is 47.6. Okay, so here you need to apply the Boyle's law for finding this. You try it on your own, and the next question also I am showing here. You have to try these two questions. I am going to explain the solutions in the next lecture. Okay, I hope you have enjoyed the session. Thank you so much.